Hello students, welcome to MemoNeet. This is Ravikant, the physics teacher. Hope you are doing well and you did well in your BTS examinations, right? And if you did well or if you are not able to do well in both the cases, I would suggest you to go for the PYQ book which MemoNeet is offering. Why I suggest you to go for the MemoNeet PYQ book is because the questions in this are so placed that it will help you to understand the strategy by which the NTA frames the question paper. Along with it, for every question, the explanations are given written in such a manner that it will help you to have a better understanding of the question and a better understanding of the approach of the questions, as well as you will understand each and every step of the solution, and it will help you to strengthen your concepts, right? So go for this PYQ book or offered by the memory, offered by memory, right? So let's begin with today's chapter. The topic for today's BTS is for B is the syllabus of BTSA, which is magnetic effect of current and magnetic, right? So we'll start with the magnetic effect of current. To begin with the magnetic effect of current, we will begin with an experiment which was being done. And what was the experiment? In the experiment, a thick wire was being taken, and to this thick wire, a battery was being connected. Right? Now, suppose this is the battery, and this battery is connected to a thick wire. Now, as soon as the key is being, let's draw a key also. As soon as the key is being closed, what will happen? A current I will flow through this conductor, right? When the current is flowing through it and we bring a compass close to this, what we find that the compass is showing some deflection, right? Now, when the key is open, right? When we open the key, the circuit is also open. When we open the key, the circuit is also circuit open, and there is no current flowing in the no current flowing in the conductor, and we find that there is a no deflection in the compass, right? So what we find here is what we conclude is that when a current flows in the conductor, there is a magnetic field formed around the conductor, right? As soon as the current is being withdrawn from the conductor, this magnetic field disappears. So from here we conclude that whenever a current flows through a conductor, there is a magnetic field formed around. So to calculate the magnetic field intensity and to understand it better, a law was being given for it, and that law is which we are going to study today. The very first topic is Biot-Savart's law, right? Biot-Savart's law. This law talks about the magnetic field intensity because of a current carrying wire. Suppose this is a current carrying wire, and the current in this wire is I, and we need to calculate magnetic field intensity at this point P, right? We will consider a small element dl out of this entire length of the conductor. So with respect to this dl, the position of this point P would be this. So we will take this as the position vector of point P with respect to the current with respect to this length element dl, right? The current is flowing in the upward direction, in this direction, right? So angle between this direction, that is the direction of the flow of current, and the position vector of the point P, let it be theta, right? So what Biot-Savart law says that small magnetic field intensity dB because of this element dl is directly proportional to the current flowing through the element which is I, and this dB is directly proportional to the length of the element, that is dl. This magnetic field intensity B is directly proportional to sine of the angle, that is sine theta, That is, theta is the angle between the position vector and the current, direction of current, and this magnitude intensity dV is proportional to 1 upon r square, where r is the magnitude of the position vector or the distance of point P from the element. What is this element called as? This element we call it as current element, right? And this current element is denoted by IDL. IDL. This is known as current, right? So when we combine this, combining this, we'll get dB is proportional to I dl sin theta upon r square, right? To remove this proportionality, we'll multiply with the proportionality constant and the equation becomes dB, let's not write it here, it becomes dB is equals to mu naught upon 4 pi I dl sin theta upon r. Now this mu naught upon 4 pi is the proportionality constant over here, in which we have our mu naught as permeability of free space, which has the value of 4 pi into 10 to the power of minus 7, right? 10 to the power of minus 7. Therefore, this quantity, that is mu naught upon 4 pi, has a value of 10 to the power of minus, right? 10 to the power of minus 7. So finally we get an expression as dV is equals to mu naught upon 4 pi I dl sin theta upon r square. So if I multiply this with r upon r, what will this become? This will become as dB is equals to mu naught upon 4 pi I dl r sin theta upon r cube, right? Or we can write it as dB vector is equals to mu naught upon 4 pi I dl vector cross r vector upon r, right? Cube. So this is the expression for magnetic field intensity SPP at a distance r from a current element IDL in a vector form, right? We are having the expression in the vector form, right? So we have found the expression in the vector form. Now let's see few more things, that if we have dB is equals to mu naught upon 4 pi I dl sin theta upon r square, then if theta is equals to 0 degree, theta is equals to 0 degree means the point P lies along the conductor. In that case, we know that sin 0 is equal to 0, then the magnetic field intensity at this point will also be equal to 0. Now, if theta is equals to 90 degree, then sine theta is equals to 1, then your dV will be equals to, that is, the magnetic field intensity dB will be equals to mu naught upon 4 pi I dl upon r, right? This is for different angles of theta. So we did the magnetic field intensity in vector form, and we have also seen the theta, right? So if you look closely, what we find is this dB, that is expression for the magnetic field intensity by Biot-Savart's law, that is mu naught upon 4 pi I dl sine theta is somewhat analogous to the equation for force, or the equation for force which we studied in your Coulomb's law, which was 1 by 4 pi epsilon naught q1 q2 upon r square. q1 q2 is replaced by ideal sine theta. 1 by 4 pi epsilon naught is replaced by your mu naught upon 4 pi, and r square is there as it is because both are non-contact forces, right? So if we talk about electric field intensity was given as E is equals to 1 by 4 pi epsilon naught q upon r square. So we can see the analogy very clear over here. This is proportionality constant. Here we have mu naught upon 4 pi as proportionality constant, right? Now in place of q, here we have ideal sine theta and upon r. So this magnetic field intensity is very much analogous to the electric field intensity, right? So we can easily remember it if we remember the Coulomb's law, right? If we remember the Coulomb's law, we can easily remember it. Now, one more point to remember is that we have 1 by 4 pi epsilon naught as 9 into 10 to the power of 9, right? And mu naught upon 4 pi as 10 to the power of minus 7, right? 10 to the power of minus. So if we divide both the quantities, that is mu naught upon 4 pi when divided by 1 by 4 pi epsilon naught, this would give you mu naught upon 4 pi into 4 pi epsilon naught. This 4 pi cancels out, and this would be equals to mu naught into epsilon naught. This will be 10 to the power of minus 7 upon 9 into 10 to the power of 9, right? So from here we can write mu naught into epsilon naught, mu naught into epsilon naught is equals to 1 upon 9 into 10 to the power of 16, 16, or we can write it as 1 upon 3 into 10 to the power of 8 whole square, right? What is 3 into 10 to the power of 8? 3 into 10 to the power of 8 is nothing but the velocity of light in free space. So we can write mu naught into epsilon naught is equals to 1 upon c square, or we can say that c is equals to 1 upon under root of mu naught into epsilon. So this is one of the very important relationships for your competitive examination. We get numericals on this, and we get some other objective type questions from this, right? So this is an important expression, that is C is equals to 1 upon under root of mu naught into epsilon, right? Now then moving forward, the next thing which we have to see is your magnetic field due to a long straight current carrying conductor. So we are not concerned about the derivations over here. So we'll simply see or go through this, that is the magnetic field because of a long current carrying conductor. Magnetic field due to a long straight current carrying conductor. Now suppose this is a straight current carrying conductor, it has current I, right? And we need to calculate the magnetic field intensity at this point P. This point P. Now let's consider a small element dl over here. Then the position vector of this P would be this, and we'll take it as R vector, right? The shortest distance of this point P from the wire, shortest distance of this point P from the wire, let it be A. The angle the point P makes with one end of the wire be this angle be phi phi 1, and this angle be phi 2, right? This angle be phi 1, and the upper angle will be phi 1, and the lower, sorry, upper angle be phi 2, and the lower angle will be phi 1, right? If this is the case, then the magnetic field intensity because of this current carrying wire at this point P is being given as B is equals to mu naught upon 4 pi I upon A into sine phi 1 plus sine phi 2, right? This is the expression for the magnetic field intensity due to a straight current carrying wire of a finite length. B is equals to mu naught upon 4 pi I upon A sine phi 1 plus sine phi 2, where A is the shortest distance of the point P from the wire. I is the current flowing in the conductor. Sine phi 1 is the angle from angle of depression, you can say angle of depression of the lower end of the wire from point P, and phi 2 you can say is angle of elevation of the point the one upper end of the wire from point P, right? Now suppose if this is a wire and we are standing over here, right? That is near the bottom of the wire. In that case, what will happen? In that case, phi 1 will be equals to 0 and phi 2 will be equals to 90 degrees. So when we put phi 1 is equals to 0 and phi 2 is equals to 90 degrees, what will be the expression? Expression will be B is equals to mu naught upon 4 pi I upon A sine phi 1, that is sine 0 will be 0, then sine phi 2, that is sine 90 will be 1. So it will be B is equals to mu naught upon 4 pi I into I upon A. Now again, suppose we take that this is the wire, is of finite length. This is the midpoint of the wire, and the point P lies exactly at the in front of the midpoint of the wire, right? So These will be the two angles subtended by the ends of the wire. So this will be 45 degrees and this will also be equals to 45 degrees. 45 degrees as 45 degrees, right? So if the length of the wire is equals to L, right? This length will be L by 2 and L by 2 and this is A, right? This is A. So for this we will have B is equals to mu naught upon 4 pi I upon A 2 times of sine 45, right? 2 times of sine 45. So this will be equals to mu naught upon 4 pi I upon A root 2, right? I upon A root 2. It will be equals to B is equals to root 2 times of mu naught upon 4 pi I upon A, right? I upon A. Now, one more case. This the same case can be also seen like this. If this is a conductor and the length of the conductor is L and this is the perpendicular bisector of the conductor and the point P lies on the perpendicular bisector of the conductor, right? And this these are the angles phi 1 and phi 2, and because this is a perpendicular bisector, for this case phi 1 will be equals to phi 2 and let it be phi. Then our expression will become B is equals to mu naught upon 4 pi I upon A into 2 times of sine phi. And what will be sine phi? This, if we look into this triangle, right? This is L by 2, this is A, and then this will be equals to under root of L by 2 whole square plus A square. So sine phi will be equals to perpendicular, that is L by 2 upon hypotenuse, that is L by 2 whole square plus A square. We put this value of sine phi over here and then we get the expression as B is equals to mu naught upon 4 pi I upon A into 2 times of L by 2. So this will give you L upon under root of L by 2 whole square plus A square, right? Then this will be expression. So there are different cases. Putting the different values of phi 1 and phi 2, you will get the magnetic field intensity because of a straight conductor. One more case we can consider. Suppose this wire is of infinite length. We do not have the length with us, right? And there is a point P at which the magnetic field is to be calculated. So if it is of infinite length, then phi 1 is equals to phi 2 is equals to 90 degrees. Because if something is of infinite length, to see its one of the end, we have to see perpendicularly upwards. So the angle will be equals to 90 degree with respect to this line A. Right? This angle will be equals to 90 degree. So putting this value as 90 degree, will get B is equals to mu naught upon 4 pi I upon A into 2, because sine phi 1 plus sine phi 2 will be sine 90 plus sine 90, and sine 90 is 1, so it will become 2. So here this 2 and this 4 goes off. What we are left with is B is equals to mu naught upon 2 pi I upon A, right? This is the case when the length of the wire is infinite. Okay? For infinite length of wire, for infinite length of. So what we have written in this till now is the magnetic field intensity because of a straight long current carrying conductor is given by mu naught upon 4 pi I upon A into sine phi 1 plus sine phi 2, right? And I hope till now you have understood what is sine phi 1 and phi 2. Accordingly, the values of phi 1 and phi 2 are placed over here and we'll get the value of magnetic field intensity, right? Magnetic field intensity. Now, once we calculate the magnitude of the magnetic field intensity, we also need to know what is the direction of the magnetic field intensity because of the long current carrying wire. So, if we are having a long current carrying wire, suppose this is the long current carrying wire and the tip of the pen shows the direction of the current. Then to find the direction of the current, we will be using Maxwell's right hand thumb rule. What is Maxwell's right hand thumb rule? Maxwell's right hand thumb rule says that if the current is flowing in a conductor and we require to find the direction of the magnetic field intensity, then you hold the conductor in such a way that the thumb of your right hand points in the direction of the flow of current. Then the direction in which your fingers curl, in that direction is the magnetic field intensity. So suppose the current flowing in the conductor is in upward direction. So if I hold the conductor in such a way that my thumb is pointing in the upward direction, then the fingers curl in anti-clockwise direction. Therefore, the current, because of the current flowing in the upward direction, the magnetic field intensity will be in anti-clockwise direction. That is, if the current is flowing in the upward direction, the magnetic field intensity will be in anti-clockwise direction, right? Magnetic field intensity will be in anti-clockwise direction. So this is Maxwell's right hand thumb rule. It is right hand thumb that you are supposed to hold the conductor in your right hand and placing your thumb in such a way that the thumb points in the direction of the current. Then the curl finger will give you the direction of the magnetic field, right? So let's see one numerical regarding this magnetic field intensity due to a straight current carrying conductor. This numerical says that a long wire with a small current element, of length 1 centimeter is placed at the origin and carries a current of 10 ampere along the x-axis, right? Find out the magnitude and direction of the magnetic field due to the element on the y-axis at a distance of 0.5 meter from it. So, if this is our coordinate system, let's say uh, this is our coordinate system, then the wire is kept in such a manner that DL is here at the origin. DL is here at the origin and the current is flowing in this direction along the x-axis, right? The length of the element is 1 centimeter, that is DL is equals to 1 centimeter. A long wire with a small current element of length 1 centimeter is placed in the origin and carries the current of 10 ampere. So the current I is equals to 10 ampere along the x-axis, right? Find out the magnitude and direction of the magnetic field due to the element y-axis at a distance of 0.5 meter. So the point P over here is on y-axis and the distance, this distance is equals to 0.5 meter. 0.5 meter, it means we have the value of A as 0.5 meter. So this 1 centimeter is equals to 1 centimeter is equals to 1 into 10 to the power of minus 2 meter, right? So first, if we look into the direction, if I hold the current carrying conductor in my right hand, placing my thumb in the direction of the current, what I'll find that my fingers are coming out of the screen, right? Coming out of the page. So the direction of the magnetic field will be in the direction at P. It will outwards. At P, the direction will be outwards. So first, the direction is this. B is outwards, right? P is outwards. Now we need to calculate the magnetic field intensity at this point. So we'll use the Biot-Savart's law. Biot-Savart's law says that your dB is equals to your B is equals to mu naught upon 4 pi I dl sin theta upon r square, right? So your B is equals to 10 to the power of minus 7, I is 10, dl is 10 to the power of minus 2, sin theta is 90 over here, theta is 90 over here, so we'll leave it like as it is. And what is the distance of the point P from the current element? It is how much? 0.5 meters. 0.5 meters will give you 0.25. Removing the decimal, just 10 to the power of minus 2 goes off. What we are left with is B is equals to 10 upon 25 into 10 to the power of minus 7 Tesla 5552. So this is B is equals to 0.4 into 10 to the power of minus 7 Tesla. So this is the magnitude of the magnetic field intensity, at this point P, right? So this is the solution of the question, right? So we have I is equals to 10 amperes, dl is equals to 10 to the power of minus 2 meters, and your r is equals to 0.5 meters, and theta is equals to 90 degree. Putting it the value, that is B is equals to 100 upon 4 pi I dl sin theta upon r square, we get the value as 0.4 into 10 to the power of minus 7 Tesla, right? Let's see one more numerical. The numerical says that use Biot-Savart law to obtain the expression for the magnetic field at the center of a coil bent in the form of a square of side 2A carrying current I. Alright, so we have a coil which is bent in the form of a square. We try to make a square. Yeah. This is a square, and the side of the square is equals to 2A. 2A, right? Now suppose a current I is flowing in the conductor or in the coil in this direction, in the clockwise direction, let's say. Then if we talk about the direction of the magnetic field, if we check from all the four sides, from all the from all the four sides, what we find that for all the four, see, for this side inwards, then for this side it's inwards, from this side it's also inwards, and from this side it is also inwards. For all the four sides, at the center of the coil, the magnetic field intensity will be inwards. The magnetic field intensity will be inwards, right? Now if we consider this as a rod of finite length, then this angle will be equals to 45 degrees, right? So if I draw it like this separately, one side of the conductor, the length is 2A, and the midpoint of this length will be A, this length will be A, and this angle will be equals to 45 degrees, and this angle also will be equals to 45 degrees, right? Because it's a square. Now if this is a square and these angles are 45 degrees, so what we conclude from here is that is phi 1 is equals to root is equals to 45 degree. And for a straight current carrying conductor, we have the formula V is equals to mu naught upon 4 pi I upon A I upon A into sine phi 1 plus sine phi 2. Now what is A? A is the distance of the point P from the conductor. So this length will be equals to A, right? Because the side of the square is of 2A length. So this length will be equals to A, right? So now putting the values, what we get, will get B is equals to mu naught upon 4 pi I upon A is A, and this will be equals to into root 2. Why root 2? Let me write it. It will be 2 into sine 45, and sine 45 is 1 by root 2. So this is written B is equals to root 2 times of mu naught upon 4 pi I upon A, right? I upon A. So this is because of one of the conductors, right? This is because of one of the conductors, and there are four conductors. So if we multiply this by 4, so this is 4 times of B, or you can write it as B net at the center of the square is equals to 4 times of the B, that will be equals to, you can write it as mu naught upon pi, because 4 and 4 cancels out, root I, root 2I upon A, root 2I upon A. So B net, the net magnetic field at the center of the coil, which is in the shape of a square, is equals to mu naught upon pi root 2 I upon A. Clear, right? So what we have done is we have simply used the formula, that is the formula for the current carrying conductor magnetic field due to a current carrying conductor of length of finite length, that is B is equal to mu naught upon 4 pi I upon A into sine phi 1 plus sine phi 2, right? Let's see which numerical is the next numerical. The plane of a coil. Okay. So this was about the magnetic field because of a current carrying conductor. Again, the direction of the magnetic field is being given by the Maxwell's right hand thumb rule. What is the Maxwell's right hand thumb rule? Maxwell's right hand thumb rule is that you are supposed to hold the conductor in your right hand in such a way that your thumb points in the direction of the current flowing in the conductor. Then the direction in which the fingers of your hand curl will give you the direction of the magnetic field because of that current carrying conductor, right? So if the current is flowing in the upward direction, the magnetic field will be in anti-clockwise direction, and if the current is flowing in the downward direction, the magnetic field will be in the clockwise direction, right? Now let's see the magnetic field. So now let's see the magnetic field due to a current carrying loop. Now if suppose we have a loop of current, suppose this is a loop, right? Suppose this is a loop, right? And this is the center. Let the radius of the loop be equals to A, and we need to calculate the magnetic field energy at this point, that is the center of the loop. And we select a current element dl over here. Then the distance of the point P from the dl is taken as r, and this r would nothing but equal to A, right? Now, if the current is flowing in this, let's say, is in anti-clockwise direction, then at this point, the direction of the current will be like this as a tangent, and R is along radius. So the angle between them is 90 degrees. So from here we get theta is equal to 90 degrees, right? So by Biot-Savart's law, we can say that dB is equal to mu naught upon 4 pi. Current is I, dl. Then sine theta is, we can write it as sine 90 upon r square, right? So r square, that is r, this is nothing but a. So we will write it as a now. So it will become b is equals to mu naught upon 4 pi I upon a square, right? Sine 90 is 1 integral dl. So if we integrate this dl, it would be equal to the circumference of the loop. So integral dl will be equal to 2 pi a. So we can write it as b is equal to mu naught upon 4 pi I upon a square into integral dl is equal to 2 pi a. So from here a and a cancels out, 2 pi and 4 pi cancel out, giving you 2. So finally we get b is equals to mu naught upon 2a, mu naught I upon 2a, right? So this is the magnetic field intensity because of a current carrying loop. And if we talk about the direction, if the current is in anti-clockwise direction, then the magnetic field in the center will be inwards. And if the current direction is in the clockwise, then the magnetic field intensity will be outward. This is inwards and this is outward, right? For clockwise current, the magnetic field intensity is inwards and sorry. For clockwise, the magnetic field intensity is outwards, and for anti-clockwise, the magnetic field intensity is inwards the plane containing the loop, right? Anti-clockwise inside, clockwise outside. Now suppose we are having a loop of current. This is the center and this is the axis of the loop. Again, the radius of the loop B equals to A, right? And the distance of point P at which we are supposed to calculate from the center is equals to R, and this point P lies on the axis, right? And we consider a element dl. For this case, the magnetic field intensity, I'm not deriving the entire thing, we get it as B is equal to mu naught upon 2 I into A cube upon R square plus A square whole raised to the power of 3 by 2, right? Mu naught I A square, it's A square 2 into R square plus A square whole raised to the power of 3 by 2, right? Where A is the radius of the loop and R is the distance of the point P from the center of the loop, right? So this is the magnetic field intensity because of a current carrying loop at a point on the axis of the loop, right? This is the expression for it. That is V is equal to mu naught upon 2 I A square upon R square plus A square raised to the power of 3 by 2, right? So from this itself we can get the above expression, that is for the magnetic field intensity at the center of the loop. At the center of the loop, this R will be equal to this R will be equal to 0. And so when if we put R equals to 0 here, if we put R equals to 0 here, we will finally get the same expression as this. Now for both the expressions, if the number of loops is equal to n, so this expression will become as B is equals to mu naught n I upon 2a, that is what if n number of turns are there in the loop, and for this also, this will become B is equals to mu naught n I a square upon 2 r square plus a square whole raised to the power of 3 by 2. So, and we multiply with the number of turns. For each turn, we'll have the magnetic field, and if we multiply with the n, that is the number of turns, we'll get the total magnetic field intensity, right? So just to understand it better, let's see a numerical. Yes, the numerical says that the plane of a circular coil is horizontal, right? It's horizontal. Now it has 10 turns. 10 turns means your n is equals to 10. N is given as 10 turns, each of radius. Your A is equals to 8 centimeter, which is equals to 8 into 10 to the power of minus 2 meter. A current of 2 ampere flows, that is I is equals to 2 ampere flows through it. The current appears to flow clockwise. Current is flowing in a clockwise direction. It means the magnetic field will be in the outwards direction, sorry, inward direction. Yes, magnetic field will be in the inward, right? Magnetic field will be in the inward direction. From a point above the coil. Now find the magnitude and the direction of the magnetic field at the center of the coil due to the current. So the magnetic field at the center of the coil is being given as B is equals to mu naught N I upon 2A. So putting the values we get B is equals to mu naught is 4 pi into 10 to the power of minus 7 into N is 10 into I is equals to 2 upon 2 into 8 into 10 to the power of minus 2, right? So this 2 and 2 goes off, 10 to the power of minus 2 makes it 10 to the power of minus 5, and this 10 makes it 10 to the power of minus 4, and this 4 ones are 4 twos are. So what we are left with is B is equals to 0.5 pi into 10 to the power of minus 4 Tesla, right? B is equals to 0.55 into 10 to the power of minus 4 Tesla. So this is the answer for this question. So what we have done, simply we have used the formula, direct formula based numerical, that is B is equals to mu naught and I upon A and I upon 2A, and all the quantities have been given in the question. Directly putting the values, you will be answer, right? So let's see one more numerical. They say that the magnetic field due to the current carrying loop of radius 12 centimeter at its center is this much. Then find the magnetic field due to this loop at a point on the axis at a distance of 5 centimeter from the center. So what they say is that B at center is equals to 0.5 into 10 to the power of minus 4 Tesla, right? And the radius of the loop, that is A, is equals to 12 into 10 to the power of minus 2 meter. They are asking us to find the magnetic field of the loop at the point on the x-axis at a distance of 5 centimeter. That is R is equals to 5 into 10 to the power of minus 2 meter. Now if you see that magnetic field at the axis is given by mu naught upon 2 I into A square upon R square plus A square whole raised to the power of 3 by 2, right? And B at center is given as mu naught I upon 2A. Now if we divide both the equations, what we'll get? From here we'll get B at axis upon B at center is equals to mu naught I a square upon 2 r square plus a square whole raised to the power of 3 by 2 into 2a upon mu naught I. So this mu naught I cancels out this mu naught I. This 2 cancels out this 2. What we are left with is b at axis upon b at center is equals to a cube upon r square plus a square whole raised to the power of 3 by 2. Right? So from here we can say that b at axis is equals to a cube upon r square plus a square whole raised to the power of 3 by 2 into b at center. Right? So now putting the value, what we get that b at axis is equals to a is 12 and r is 5. A is 12, so 12 into 10 to the power of minus 2 cube upon 5 into 10 to the power of minus 2 whole square plus 12 into 10 to the power of minus 2 whole square, and this whole raised to the power of 3 by 2 into 0.5 into 10 to the power of minus 4. Right? This is the thing. Then putting the values and solving it, will get b at axis. When we solve the above expression, we will get b at axis is equals to 3.9 into 10 to the power of minus 5, 3.9 into 10 to the power of minus 5 Tesla. Right? Calculation can be done, and it comes out to be 3.9 10 to the power of minus 5 Tesla. What I'm trying to make you understand is that most of the numericals coming from magnetism and magnetic effect of current are, if you talk about the numericals only, are directly formula based. If you remember the formula very well for what case of which formula is to be used, you can easily solve the numericals, right? So better remember the formula. So let's move ahead. We have seen the circular loop, we have seen the straight wire. Now what next we have to see is your Ampere circuital law, right? Ampere Ampere's circuital law. Ampere's circuital law, right? So I will start with the statement that this Ampere circuital law is analogous to Gauss law, which we have studied in your electrostats. And what in electrostats says that closed integral E dot dA, closed integral E dot dA is equals to Q upon epsilon naught, right? Q upon epsilon naught. So here in magnetism, we know epsilon naught is being replaced by mu naught, Q is replaced by I, so and E is replaced by V. So putting the analogy, or you just understand that the Ampere circuital law says that closed integral B dot dl is equals to I into mu naught, right? Closed integral B dot dl is equals to I into mu naught. Now, what does this statement say? This statement says that the net magnetic field passing through a closed loop is mu naught times the current enclosed in that loop, right? What Ampere circuital law says that the magnetic field, net magnetic field, because of a current carrying conductor, is equals to mu naught times the current to the conductor enclosed in a closed loop, right? Suppose here it is a conductor with current I flowing into it, right? and we draw a loop around it, and there is element BL, right? So if the current is flowing in the upward direction, the direction of the magnetic field will be in anti-clockwise direction, right? Maxwell's right hand thumb rule, the current is flowing in upward direction, the magnetic field will be in the anti-clockwise direction. So at this point, this will be the direction of magnetic field B vector, right? And the position of the R vector from the current carrying wire, this will be R. This will be R vector in this direction, right? So this will be the direction of R, and this is the direction of or B. So theta will be equals to 90 degree over here, right? So what Ampere's circuital law says that closed integral B vector dot dl vector B vector dot dl vector is equals to I into mu naught. So B, the angle between B and dl, both are in the same direction. So angle theta will be equals to angle between B and dl, that theta will be equals to 0 degrees. So that dot product will be equals to BDL. So we will write it as closed integral BDL cos 0, right? So cos 0 is equals to 1. So this will turn B closed integral DL, right? Then DL is the element of the loop around the circular loop, loop around the current carrying conductor, right? So it will be equals, and its radius is equals to how much? R. So this will be equals to B into 2 pi R, right? B into 2 pi R. Now what Ampere's circuital law says that closed integral B dot dl is equals to I into mu naught, right? So your B dot dl is coming out as B into 2 pi R is equals to I into mu naught. So B will be equals to mu naught upon 2 pi I upon R, right? This is what? This is the magnetic field intensity due to a current carrying conductor at a distance R from it, right? So from here we can see that Ampere's circuital law is closed integral B dot closed integral B dot dl is equals to mu naught into I. Right? This is the statement of Ampere's circuital law. Using the Ampere circuital law, let's see how we calculate the, or let's see the directly see the formula for the solenoid. For solenoid, right? Solenoid is, this is a core on which the wire is been bound. There is a winding around the solenoid, and let's say the current is flowing in this direction, right? So if we look from this side, the current is flowing in your clockwise direction. So from here the magnetic field will enter. And if we look from this side, the current is flowing in the anti-clockwise direction. So the magnetic field will come out of this. So this becomes the north, and this becomes the south, right? This becomes the south. So for a solenoid, the magnetic field intensity is moving from south to north inside it, and outside it, it's forming a loop and moving from north to south. Moving from north to south. And the magnetic field intensity because of a solenoid is given as V is equals to mu naught N I, right? Mu naught N I, where mu naught is the permeability of the medium, I is the current in the solenoid, and N is the number of turns per unit length, number of turns per unit length, right? So the expression for the magnetic field intensity because of a solenoid is equals to mu naught N I, right? Mu naught N I. Similarly, if we talk about toroidal solenoid is if we join both the ends of the solenoid and form a loop, right? And the winding has been done like this, right? Then the magnetic field is formed inside it. The magnetic field forms loop inside the toroid. There is no magnetic field outside the toroid. And for toroidal solenoid also, the magnetic field B is given as mu naught N into I, where again N is the number of loops per unit length. Number of loops per unit length. So let's see again the numericals from this are mostly direct formula based. So let's see one numerical out of it. Yes, the numerical says that a solenoid of length 0.5 meters. So L is being given to us as 0.5 meter and is of radius R is equals to 1 centimeter, right? Is made up of turns is 500 turn, 500 turn. It carries a current of I is given as 5 ampere. What is the magnitude of the magnetic field inside the solenoid? So magnetic field inside the solenoid is given by the formula B is equals to mu naught N into I, where N is the number of turns per unit length. So number of turns per unit length. So number of turns is 500 and length of the solenoid is 0.5. So this will turn out to be 1000. So we have capital N, capital N is equals to 1000, right? So putting the values in the formula, we get B is equals to mu naught is equals to 4 pi into 10 to the power of minus 7 into N is 1000 into I is 5 ampere, right? If we calculate this, we'll get our answer as B is equals to 6.28 into 10 to the power of minus 3 Tesla, right? B is equals to 6.28 into 10 to the power of minus 3 Tesla. This is how directly from the formula we'll calculate the magnitude because of the solenoid. Let's see one more numerical. Let's now move to the next topic, which is the force on a moving charge in a magnetic field. So if a charge is moving in a magnetic field, then definitely the charge will be moving with some velocity, and then velocity is a vector quantity, right? It is moving in a magnetic field, then again magnetic field is a vector quantity. So both of them will be having some direction. So on the basis of direction, the force on a charged particle moving in a uniform magnetic field is given as F is equals to Q, that is the charge on the charged particle is into V vector cross B vector, right? V vector cross B vector. So this can be written as magnitude of the force is equal to Q V B sine theta, and theta would be the angle between the velocity and the magnetic field. Now suppose the velocities are the magnetic field is perpendicularly inwards the plane, right? Perpendicularly inwards the plane, and the particle is moving in the direction from left to right, left to right. Then the direction of the velocity vector would be in this direction. This is v vector, and that of the magnetic field will be in the perpendicularly inwards. So while moving from V to B, that is finding the cross product of VV, we are moving in the anti-clockwise direction. So if we are moving in the anti-clockwise direction, the force on the charged particle will be perpendicular to V and in the direction upwards. And because of which it will start moving in a circular loop, right? Because the magnetic force is is perpendicular to the velocity, right? So the very first thing you are supposed to know from here is that the force acting on the charge moving in a uniform magnetic field is given by Q into V vector cross V vector, right? And this force magnitude is given as Q V B sine theta, where theta is the angle between what is theta is the angle between the V vector and B vector. Now the direction of this force is being given by Fleming's left hand rule. What Fleming's left hand rule says that if we yeah Fleming's left hand rule says that if we place our index finger in the direction of the magnetic field and B is the direction of the the middle finger is the direction of the velocity, then the thumb will denote the direction of the what direction of the force experienced by the charge particle. So here in this example, the magnetic field is in inward direction, velocity is from my left to right, then the force exerted on the particle will be in upward direction. This index finger is in the direction of magnetic field, middle finger is in the direction of velocity, and then thumb is denoting you the direction of the force acting on the particle, right? So if your F is equals to QVB sine theta, then if theta is equals to 0 degree, F will be equals to 0. That is, if the charged particle is moving in the direction of magnetic field, then there will be no force experienced by it. Then if theta is equals to 90 degree, then F will be maximum, and that would be equals to QVB, right? And if theta is equals to 180 degree, then too the force will be equals to 0, right? Force will be equals to 0, and the direction of the force will be given by the Fleming's right hand Fleming's left hand Fleming's left hand rule. Now the next thing which you have to know is the Lorentz force. Lorentz force. So what is Lorentz force? That if a charged particle is present in a uniform magnetic field and electric field simultaneously, then the force experienced by the charged particle is the sum of the electrostatic force and the magnetic force experienced by the charged particle, the magnetic, right? Electrostatic force magnitude is equals to Q into E, where E is the electric field intensity, and Sm, that is magnetic force magnitude, will be equals to QVB, right? QV V vector cross B vector, right? V vector cross B. So the Lorentz force F will be equals to Q into E vector plus V vector cross B vector. This is what is Lorentz, right? This is what is Lorentz force. Now let's see one numerical on this. It says an electron is moving. It's an electron, not electron. It's an electron. An electron is moving northward with a velocity of 3 into 10 to the power of 7 meter per second in a uniform magnetic field of 10 Tesla directed eastwards. Find the magnitude and direction of the force on the electron. As per the question, if we take the reference of the direction as this is the reference north, this is east, this is south, and this is west, right? So according to them, the velocity is electron is moving in the northward. So this is the velocity v, and the magnetic field is in the direction eastward. So this is the magnetic field B. So from here it is clear that theta is equal to 90 degree, right? Now if we need to find the direction of the force experience, index finger is in the direction of the magnetic field, middle finger is in the direction of the velocity, and thumb denotes the direction of force. The force will be inward. So the direction is inwards. Now if we need to calculate the magnitude, then magnitude F is equals to QBB sin theta. So electron has a charge of 1.6 into 10 to the power of minus 19 coulomb into B is 3 into 10 to the power of 7 into B is 10. B is 10. So this would be equals to 4.8 into 10 to the power of minus 11 Newton, right? 4.8 into 10 to the power of minus 11 Newton. So simply again using the formula F is equals to QVB sin theta, putting the values we get the direction as well as the force magnitude experienced by the electron, right? Now let's see. Alright. Now let's see one more thing. Now if suppose, which is the example which I gave you, that suppose if the magnetic field is directed inwards inside the paper, perpendicularly inside the paper, and the charged particle Q moves with the velocity v from my right to left. Now in this case, the magnetic field is directed inwards, velocity is in this direction, that is from my left to right, then the force acting on the particle will be perpendicularly upward. Now if this is the direction of the force, now this force will act as a centripetal force and will force this particle to undergo a circular, right? And when the particle undergoes a circular motion, that circle will have a radius, right? This circle will have a radius. Now this centripetal force F is nothing but equals to QBB sin theta. Sin theta is 90 degrees, so QBB, and this is acting as a centripetal force, so I can equate it to as mb square upon r, where m is the mass of the charged particle, right? So if I need to calculate the radius of the circular path followed by the charged particle, then r will be equals to mb upon qb. This is the radius of the circular path followed by the particle when it is moving in a uniform magnetic field and the direction of velocity is perpendicular to the magnetic field. Then the force experienced by the particle will also be perpendicular to the velocity, which will result in the circular path followed by the particle, and the path of the radius of the circular path is given as r is equals to mv upon qb, right? So the time period of repeating the circular motion will be equals to 2 pi r upon v. So this will be equals to 2 pi upon v, and r is your m v upon q b. So this v and v cancels out and we get time period t is equals to 2 pi m upon q b. 2 pi m upon qb. Now what we need to understand from here is that this time period for a given charge particle is constant. Why it is constant? That 2 is constant, pi is constant, mass of the particle is not going to change at that instant, so mass is also constant. Charge on the particle is also not going to change at any instant, so it is also constant, and the magnetic field which you are providing is also constant. So this all the variables involved or all the factors involved in this time period are constant. Then for a given charge particle in a given uniform magnetic field, the time period of its oscillation or the time period of its circular loop or path of a circular loop is a constant, right? So if we increase the velocity of the particle entering into the magnetic field, if we increase the velocity of the particle just to maintain the time period, because the time period is not dependent on the velocity, it is dependent on the mass and the charge and the magnetic field, which are constant. So just to maintain the same time period, if the velocity increases, radius of the circular path will also increase, right? So whenever a charged particle enters in a magnetic field and undergoes a circular path, then that circular path has a radius is equal to mv upon qb, and the time period of the circular rotation is t is equal to 2 pi m upon qb, which is a constant. And if we increase the velocity of moving charged particle in the magnetic field just to maintain the same time period, the radius of revolution or the rotation or the path of the radius of the path of the circular motion will increase. That is to maintain the time period of the circular motion. So from here we have two formulae. One formula is R is equals to mv upon qb. This is the radius of the circular path, and time period t is equals to 2 pi m upon qb, which is a constant value for a given moving charge, right? So let's see one more numerical here. Yeah. So the numerical says that an electron, after being accelerated through a potential difference of 10 to the power of 5 volts, so if an electron has a charge Q is equals to E 1.6 into 10 to the power of minus 19 coulomb, is being accelerated by a voltage of V is equals to 10 to the power of 4 volt, enter the uniform magnetic field, B is equals to 0.04 Tesla, perpendicular to its direction, that is theta will be given as 90 degrees. Calculate the radius of curvature of the target. So radius R is equals to what? mv upon qb, right? mv upon qb. So the mass of the electron is 9 point. Mass of the electron has been given. See, this is the velocity and this is the voltage. Right? So mass of the electron we know that is 9.1 10 to the power of minus 31. B we do not have with us. Q we know. B we know. So we do not know V. Now if the charge is moving with some velocity, then it will have kinetic energy that is equal to half m v square, and this kinetic energy will be equal to Q into V, that is equal to half m v square is equals to your 1.6 into 10 to the power of minus 19 into 10 to the power of 4, right? So we can say from here that v square is equals to 1.6 into 10 to the power of minus 19 into 10 to the power of 4 upon 9.1 into 10 to the power of minus 31. So V will be equals to under root of 1.6 into 10 to the power of minus 19 into 10 to the power of 4 upon 9.1 into 10 to the power of minus 31. This is the value of V. So to calculate, in order to calculate the radius, R will be equals to your m is 9.1 into 10 to the power of minus 31 into V, the value of V will take it from here, upon Q is 1.6 into 10 to the power of minus 19 into B is being given to us as 0.04 Tesla, right? 0.04 Tesla. Putting the values and when we calculate, we get R is equals to 8.43 millimeter. 8.43 millimeter. So again, simply if you remember the formula, it is directly formula based. The only thing over here extra over here is that you should remember, since you did not get the velocity directly, indirectly with the help of the kinetic energy, they have given us the velocity, right? Sorry. So calculating the velocity from here and putting the value of velocity calculated from here in the formula mv upon qb will simply get the magnitude of the radius of the circular motion followed by the charge point, right? So I hope I made most of the concepts in this lecture clear to you all, right? This is all from my side for this session, right? And I hope, yes, this is all from my side from this session, and I hope that things are clear to you all. And if still you have any doubt and if you have any suggestions to give, please write in the comment box, and please do go through the entire video, and after seeing the video, please go and solve the numericals, practice the numericals, go for the P by Q book. There you can see how the numericals are coming from this chapter, and then have a good practice, and then you will see the next part in our the more other topics in the next part of our video. So this is all from my side today, right? Thank you.